Okay, so now that we've defined work and kinetic energy, and we looked at how work can change kinetic energy, let's look at some of the other things, or the other kinds of work we can do on an object, or the work done by things like gravity or some other forces. Okay, so we'll start with that. Let's look at what happens when we calculate the work done by gravity. Okay, so visually, the idea would be you have an object of some mass, okay, and it's falling, so we're going to give it some points of reference. It starts at y0, it falls to another point y1. Okay, now the only force causing it to fall is gravity. So how much work is gravity doing? Okay, so if we use our general work equation, it's an integral of the force times the displacement, which in this case is along the y-axis. Okay, and we know, let's see, the limits. We start at a position y0 and we end at the position y1. The force is gravity, so that's minus mg. Okay, and we're only doing this because we know we are close to Earth's surface. Okay? That's important because if we were not near the surface, we'd have to use a different equation. Okay, so for right now, we're close to the Earth's surface. Okay, and this is over a displacement in the y. So if we do the integral of this, mg is a constant, so we're really just taking an integral from y0 to y1 of dy. Okay, so all that means is the antiderivative of nothing, or 1, is y. So we're going to evaluate that between y0 and y1. Okay, so we end up getting minus mg y1 minus a negative mg y0. Okay, so those two negatives are going to cancel, so it's minus mg y1 plus mg y0. Now that term, mgy, is actually defined as the gravitational potential energy. Okay. And you'll typically see it written as a capital U and then a subscript for G for gravitational energy. Okay. And it's an energy, so just like kinetic energy, its unit is in joules. So what we find is the work done by gravity. Okay, notice, to calculate a change in something, it's final minus initial. Okay, but when we look at our expression, we didn't get final minus initial, we got negative final plus initial. Okay, so what does that mean? That changes our usual definition and tells us that the work done by gravity is actually a negative change in gravitational potential energy. Okay? Now, that's important because, and by what's important, I'm referring to the negative sign out front. Okay, because what that means is, okay, recall from the last video that work is a change in kinetic. Okay, so if the change in kinetic is positive, the question is, where did that kinetic energy come from? Now, in the case of gravity, if gravity caused an object to fall and move faster, what must have happened? It must have gained kinetic energy, and that energy must have come from losing potential energy. So that's why in this equation there's a negative sign, because if gravity caused an object to speed up, it gave it kinetic energy. Where did it come from? It came from potential. So if you gained kinetic, you lost potential. That's why it's a negative sign. All right, and then the other kind of potential energy that we can talk about
involves the use of springs. Now, rather than redoing all the math for finding the work done by a spring, I recommend that you go back and you look at the Work and Energy video 3, where I work through how to calculate all the energy that's stored in, or rather how much work is done by a spring to move it from one position to another from equilibrium. And so when it comes to the energy though, if you think about it, as you compress or stretch a spring, the further away from equilibrium you get, the more restoring force you are providing that spring to fight back. In other words, the more you stretch or compress, the more potential energy you are storing in the spring. So let's go back into the video at the part you didn't see.
So from here we've defined a new expression. The 1/2 k change in x squared is actually defined as the elastic potential energy. Okay, which, just like in gravitational potential energy, we use a capital U for potential. Now the subscript might be misleading. You would think if it's elastic potential energy, we would use an E, but that gets mistaken for electric potential energy. So instead, we use a lowercase s because it's for spring or something that can stretch, compress. So that's the expression for it's elastic potential energy. And just like all energy, its units are in joules. So that means that the work done by the spring is actually a negative change in elastic potential energy. And so just like when we did gravitational potential energy, it's the same reason. As the box is gaining kinetic energy, where is it getting from? So kinetic energy is increasing, which means the potential energy of the spring must be decreasing by the same amount.